Okay, so in this video, we are going to learn about flood measurement and forecasting. And in order to do that, we need to know about hydrographs. So hydrographs is a graph. It's a graph of a river's discharge. So we have river's discharge or stage, or basically it's the height of water level in that river versus time. Okay, and the way we measure those two variables, we actually can get those two variables using stream gauges that we install in rivers. And here is an example right here of a stream gauge on the river. Basically, again, it measures the discharge of water in the river. So discharge is basically a function of three main factors right here: the width of the river, the height of the river, or the stage of the water level, as well as the velocity of the water itself. Okay. So you have that, and then you also measure those variables in time. So therefore, you will have the discharge data as well as time data as well. So by having those different variables, we can actually plot those discharge by time. And typically during flooding, this is the shape of the curve that you will see. All right. So here would represents the start of a flooding, and then the level of the water got increases right here, and then eventually um, it actually reaches the crest first and then goes down to the normal level again. Okay, so in this case we have the location of gauge right here. Okay, in this drainage basin right here, and here this illustration is actually very nice because it actually compares the amount of precipitation, with the timing of the crest the of the flood. Okay, and it looks like there's a time delay. There's a little bit of time delay between the peak of the precipitation as well as the peak of the flooding event. Here is a real example of a hydrograph in one of the rivers in Tucson, Arizona. Okay, this is the 5-hour storm right here. As you can see here, the water level goes very, very quickly and reaches the crest of it very, very quickly. It's just within 2 hours of the start of the floods. And this is something that we don't want to happen because, um, yes, we understand that sometimes floods can occur, and then there's nothing we can do with that. But we have to do our best to actually delay the flood to reach its highest level. Okay, because if it occurs very fast or very rapidly, just like what happened here in Arizona, it happened within 2 hours of the start of the floods, then there wouldn't be enough time for people to evacuate or to get prepared and many things. Okay, so this is an example of a flash flood that happened in Colorado that rose rapidly in 3 hours. Rocky Canyon wall, steep gradient quickly funneled water toward people and towns located downstreams, and the wall of water as high as 20 feet rushed down the canyon, destroying everything, and unfortunately, it killed 145 people during the floods. Riverine floods are regional floods involving larger volumes of water than flash floods due to larger watersheds and extensive floodplains. Riverine floods commonly result from multiple rainstorms and spring runoff from melting snow. These are basically just the floods that we typically have, during storms or during anomalously high volume of water in major rivers. Such as what happened in 2005. I think I mentioned this in the previous video. We had you know um, uh, a great flood that occurred in Pennsylvania in 2005. This was caused by a major snow cover in a higher elevation in the Poconos and Catskill areas right there. Um, and it was one of the worst flooding in 50 years along that river, and it was consistent with 80 to 100-year floods. So basically, in order to minimize the risk of flooding event, scientists started to conduct flood forecasting. Okay, flood forecasts are determined by several factors. One is they typically examine the past events, when the major floods occurred, how long was it occurred, and what was the main cause for the floods. Okay, and they also measure the maximum annual discharge in order to basically better predict flooding that could occur in the future. They also rank the past events. So once they study the past events, they rank the past events, and then they extrapolate to future possibilities. So, for example, here are flood forecasting for Mississippi River that was measured at St. Louis. So, flood forecasting requires a very long-term record of annual peak discharge. So, for example, all the bars that you see here, the blue bars that you see in this picture right here in this graph, they all represents the peaks of different flooding events that have occurred since 1815, from 1850 all the way to early 2000s right here. Okay, or it probably looks like in the middle 1990s, I believe. All right, but all those bars that you see here in this picture, again, they represent the different flooding event, and from here they can actually measure that, okay, we might have some 100 event floods right here because we have this level right here, about 1000 1 million of cubic feet per second, okay, that occurred in 1903 and occurred again in 1993. So it's about a 100-year flood. So we might have a 100-year flood right here, and then we might have maybe a 50-year floods maybe in between right there, okay, and then so on. Okay, so by having these past events and then rank them accordingly, we could actually have a better understanding about the patterns, flood patterns, that can occur in certain regions, and in this case, for Mississippi River in St. Louis. And then you can plot those events into a graph like this to basically understand the recurrence intervals of those floods. So the recurrence intervals equals the average time between floods of a given size. For example, we have 100-year floods estimated size. That would be the benchmark for evaluating a river's flooding capability. And what it means by 100-year flood is that this is a flooding event that has a probability of 1 in 100 chance, or 1% probability of occurring in any year. Okay. So, for example, a 100-year flood map of Montpelier in Vermont. Okay, so this is the 100-year flood area that could happen in Montpelier in Vermont. Here, the yellow areas represents the 100-year flood event. And 100-year flood again has a 1 in 100 chance of occurring in any year. And this is something that I would like you to know, because this is a flood event that recently occurred July 10, 2023, and this happened in Montpelier in Vermont. Look how devastating the flood is. I mean, water is everywhere. You know, there are casualties as well associated with this event. with this flooding event. Look how murky the water is because it brings lots of suspended particles as well. Everything is submerged underwater. Major highways, major roads are cut off, among things. Okay, so this happened in the summer of 2023. Just recently, if you watch if you watch this video in 2023, this just happened recently. All right, so let's take a look at the hydrograph that we had in Montpelier in Vermont that happened recently in 2023. So this is again the hydrograph. This is the normal hydrograph right here on the left side. We start from the left, and then it looks like around 12 a.m. or 12 p.m. Monday, July 10, the water start to rise, okay? And it climbs all the way up here, okay? And it actually reaches the peak at about 20.88, okay? And the forecast crest was about 22.4 feet, all right? This was just below the record of 27.1. And it turns out that this level of flood actually represents the 100-year flood that just occurred in Montpelier. Not last week. I'm sorry. This was done in the summer, but it just occurred last summer. Okay. And the flood that we had in July 2023 represents the second highest on record in Montpelier. And the entire city, again, as you can see from the video, that the entire city was underwater and the state of emergency was declared. All right, so I think that's it for this video, and I'm going to we will see you again in the next video. Okay, bye bye.